We saw the simple version. Remember, we said that the simple version, we talked about the number of registers it has. We saw it had only 5 registers: the accumulator, the program counter, the status word, the register L, and then the index register. But when we came to talk about the extended version, the SIG-XE, we saw that it had 9 registers. It has the other 5, then plus register S, register T, then the floating point accumulator, okay? And then the base register, register B, okay? We talked about the addressing modes or the instruction formats. The simple SIG had only one format, which begins with an opcode. Then there is bit number 9, which is used to specify the addressing mode. And then the remaining 15 bits, those specify the address. But when we came to the extended version, we saw that it has got 4 different formats. We saw that it has 4 different formats. There is a format which we call a format 1, which is only 1 byte. And this is used for instructions which do not need the operands. So you just mention the opcode and the instruction is executed. So that is a 1 byte instruction. Then we saw that there is a format 2, which is a 2 byte instruction. Now this format has got 2 bytes. The first 8 bits are used by the opcode. Then the remaining 4 bits, 8 bits, which are divided 4-4, are for registers. So this is a format where the operands are registers. Like someone can say, add what is in register S to register T. So there is an opcode, the instruction, and then you mention the concerned registers, which we call R1 or R2. Then we saw 2 other formats, format 3, which is 3 bytes, and the format 4, which is 4 bytes. We said that format 3 and the format 4, these 2 formats are the ones used when the operand is in memory. So it means that we have to calculate the particular memory location where we are going to get data from so that it can be processed. Remember, data is always in memory. We fetch it and we bring it into the CPU for processing. But we have to identify a particular memory location where we are going to pick the data from. Or in case of storing, again, you identify that particular memory location where you are going to deposit the data. Now, this format, we said, has got an opcode which is 6 bits. Then we have some flags there, flags N, I, X, B, P, and E. And then displacement in the case of format 3. And then for format 4, which is 4 bytes, we have the opcode again, 6 bits. Those other 6 flags, and then the address. Okay, so these formats are the ones used when the operand is in memory, which necessitates us to calculate the target address, or in other words, to find the address of a particular memory location which we are interested in. Now, to remind ourselves, we saw that these bits N, I, X, B, P, E, they are all used to find out which type of memory location or where the memory location is going to be found. Okay, so to go by what I have written in the slides there, we are saying that for those instructions where you don't go to memory, remember there is a format 1 where we don't need any operand. Format 2, the operand is in registers. Remember, registers are found in the CPU, not in memory. So for instructions where you don't reference memory, formats 1 and 2 are the ones which are used. Then for memory references, we can use either format 3 or format 4. Now we begin by explaining the bits like we did. We said that in most cases, that bit E is used to identify format 3. If E is 0, it means format 3. If E is 1, it means that the instruction is format 4. Yes, Tom, what is the problem?
Yeah, so mine is not about the class. I was just requesting that you let some people in. They were in the waiting room and they wanted to enter.
Oh, I don't see them. Okay. Let me hope they are going to enter. Okay, so I was saying that that is the use of format, that bit E. And again, you remember, we said that that is one indication. When E is 0, mostly it is a format 3 instruction. But when it is a 1, mostly it is a format 4 instruction. Okay, although we will see cases where it may not apply. But another way of identifying whether it is a format 3 or a format 4, you remember, we said is just to look at the size of the instruction. If it is a format 3, then the instruction consumes 3 bytes. If it is a format 4, the instruction is 4 bytes. Okay. Okay, so we have 2 new relative addressing modes. These are the ones we use to get again to the particular memory location where we can use the base or program counter. Remember, base is mainly for when you are going to use that bit B. B is for base, and that flag P is for program counter. Okay, so how are they used? You can see there that you can calculate the target address. That means the address of a particular memory location you are interested in. So if B is 1 and P is 0, then the target address is calculated by taking what is in register B plus the displacement. Okay. But when P is 1 and B is 0, then the target address is calculated by taking what is in the program counter plus the displacement. Remember, the target address is that address where we want to get data from, if the data is in memory, or that address where we are going to deposit the data. Okay. Okay, so we have explained that. We are saying that for program counter, the addressing, it is a 12-bit signed integer. Okay, that is the displacement. Negative values are represented in the 2's complement format. Okay, Moluta, what don't you understand? What didn't you hear? Can you let me know what you missed when my phone microphone was not very clear? Yes. I'm sorry, but do you hear me now? Are you hearing me now? I hope it is a bit better.
Yes, we can hear you.
Okay.
But you pardon the other part because you were breaking the previous one.
Okay. So for the other part, you remember I said, if I can go back, you remember we have those flags N, I, X, B, P, and E. When we are trying to find out these instruction formats, you can see we have flags N, I, X, B, P, and E. And then I said that these flags are used to calculate the target address, because we have said that format 3 and the format 4 are the formats which we use when we want to, they are the formats we use when we want to access memory. That means when the operand is in the memory. Remember we said that format 1 and the format 2, the operand is not in the memory. Format 1, you only have an opcode. There are instructions where we don't need any operands. So where you don't need any operand, that is a format 1 instruction. Then in format 2, the opcode are registers. We have 2 registers. And I gave an example that this is a case where someone can give an example like add what is in register S to register T. So you get the opcode for adding, and then you mention the operands, which are registers, the S and the T. So for format 2, the operands are registers. Format 3, the operand is in a memory location, like someone would say, add what is in memory location X to what is in the accumulator. So it means you have to go to memory, find out, you first find where memory location X is, then you pick what is in that memory location, and then you add it to, you bring it to the CPU, and then you add it to the accumulator maybe. So for format 3 and the format 4, the operand is in the memory. Okay. Now, similarly, format 4, the operand is in the memory, but we say the format 3, the instruction is 3 bytes, format 4 is 4 bytes. So we said that bit E, in most cases, when E is 0, that means a format 3 instruction. When E is a 1, mostly it is a format 4 instruction. But we again said that you can find out or identify whether you have a format 3 or a format 4 by just looking at the size of the instruction. If it is 3 bytes, automatically that is a format 3. If it is 4 bytes, that is automatically a format 4. And then here, I was showing you how we calculate the target address. And we said that when the bits B is a 1 and the P.
Excuse me, sir.
Yes, please.
I beg your pardon on the E for format 3 and format 4.
I said these bits, bit E, you see both in the format 3 we have E, and then even in the format 4 we have E. So I said that when E is a 0, when that bit E is a 0, it means that the instruction is a format 3. In most cases, I'm saying we will see instances where it is not a format 3, but it is a 0. And then when it is a 1, in most cases, it is a format 4. Okay. Then we said that when you come to calculating the target address, that is when we use bits B and P. We said that when B is a 1 and P is a 0, when B is a 1, you note those bits, B means base. So when B is a 1 and P is a 0, you take what is in register B, and then you add the displacement, okay? And when P is a 1 and B is a 0, we take what is in the program counter, and then we add the displacement. That takes us to the target address, okay? Then when both bits B and P are 0, of course, that means that we are not using base and we are not using the program counter. when those two bits are 0, then it is only the displacement which is taken as the target address. So the displacement is the target address, okay? Then we have these other special cases. We are saying that for format 4, bits B and P must be a 0. So that is another indication. They have to be a 0 because you are not going to do any calculating. The address is given. If you look at the addressing mode, the format for format 4, the address is given. These 20 bits, that is the address. So there is no calculation. You don't need to calculate anything because the address of a target address, because the target address, that means the address where you are getting the operand from, is already given. Okay, so there is no calculation. Therefore, that's why they are saying that for format 4, B and P are 0, because you are not going to do any calculating. Okay. So format 4, bits B and P must be 0, and the target address is just taken from that address, which is the address of the instruction. And we call that one direct addressing, okay? But then we also said that bit X can also be used with the other addressing modes. That means it can be used with the base, or it can also be used with the program counter. And it is only used when that bit X is a 1. So if that bit X is a 1, it means you can add what is in register B plus the displacement plus the index register in case X is a 1, okay? But then we have the other bits. You remember we said there is bits I and N, okay? Now, after calculating the target address, you will get to that address, but then the question is it the address itself which is the required operand, or the contents of that particular address? So here it is bits I and N, which specify what should be picked. So if I is 1 and N is 0, the target address is the operand we need. We don't pick the contents of the target address, but we only pick the address itself. So this one is called the immediate addressing. That's when I is a 1 and N is a 0. Now, when I is a 0 and N is 1, then that is indirect addressing. You remember in indirect addressing, they give you the address, okay? You look at the contents of that address, and then the contents of that address are leading you to another memory location, okay? Whose contents is the required operand. We are going to see an example of that. Then when both I and 0 are 1, sorry, when both I and N, when they are both 0 or when they are both 1s, we call that one simple addressing. Now with the simple addressing, it is the contents which we take. It is the contents which we take. Now, another restriction here is that you can't use indexing in immediate or indirect addressing. We don't use indexing, okay? Then something else again here is that when bits N and I are both 0s, okay? When both bits N and I are both 0s, okay, I hope I am clear now, that when the bits N and I are both 0s, then it means, okay, that B, P, and E, we don't consider them as base or program counter or format 3 or format 4. All those bits are appended to the displacement, and the whole of those 15 bits now, because the displacement is always 12 bits. But if N and I are both zeros, then bits B, P, and E are appended to the displacement, and we get 15 bits. And those 15 bits become the address. They become the target address. Okay. Now that is a summary. Direct addressing. Okay. When both bits B and P are 0, you remember we said that it means that you are not going to use the base, and you are not also going to use the program counter. So it is just the displacement and maybe contents of register X. But you remember we only add the contents of register X when that bit X is a 1. Okay. Then for program counter addressing, P is a 1, B is a 0, that is the program counter. So it means you take what is in the program counter plus the displacement plus what is in register X. That gives you the target address. When B is a 1 and P is a 0, that is the base. B1, P0, that is the base. It means you take what is in register B plus the displacement plus contents of register X. Now, after getting the target address, okay, then we find out, we want to know whether it is the address we are interested in or contents of that address. Okay, so when N is 0 and I is 0, we said that is a simple addressing. Here, the contents of the target address is the required operand. But then we said that in that case, bits B, P, and E, they are the address bits. N is 0, I1, I is for me immediate. When N is 0, I is 1, that is immediate addressing. So there the target address is the operand we take. Okay. When N is 1 and I is 0, that is indirect addressing. Remember, we said that with the indirect addressing, the contents of the target address is the address of the operand. And then N1, I1, that is a simple addressing. It is the contents of the target address which we pick. Okay. Now, you will understand better with an example. Let us look at this example. I want everybody to be attentive. Now, this is an example where we assume that register B has got that numbers 006000. The program counter has that one, 3000. The index register, register X, has a 90. And then the instruction load, the accumulator, its opcode is 00. Okay. Now we have memory. They are showing us memory location. A memory location whose address is 3030. It has got its contents is 3600. Another memory location whose address is 3600. Its contents are 103000. Then there is another memory location whose address is 639, and that is its contents. Then another memory location which is 6303. Again, you can see its contents. Now, someone can give you a question. Someone can give you a question, and he says that suppose you have got this instruction, a machine language instruction, which is 032-600. 032-600. Okay? Someone might ask you, what is that instruction accomplishing? Or what is it doing? So it means here, you have to know what the instruction is doing. And then that is with the explanation you are supposed to get, okay? Now, when you are given such an instruction, I want us to go together. Please pay attention because this is a calculation. Someone is saying, we are looking at that first one, 03 to 600 is the machine language instruction. Someone might ask you to find out what that instruction is doing, okay? So when you look at that instruction, if I may ask, which format is it? Is it a format 1, a format 2, a format 3, or a format 4 instruction?
It is a format 3 instruction.
Okay, very good. That is a format 3 instruction, because when you look at the digits, this is 03 to 600. I think you can see that it is 6 digits. Okay. Now these 6 digits are hexadecimal digits. So if they are hexadecimal digits and they are 6 digits, it means 24 bits, because every hexadecimal digit is 4 bits. So that is a total of 24 bits. And then when we are discussing the formats of the instruction, we said that format 3 is the one which is 3 bytes. And you know 3 bytes is 24 bits. A byte is 8 bits. So if it is 3 bytes, that means 24 bits. So this one is a format 3 instruction. So if we are going to interpret what it does, we are going to use the format 3. Okay. Now, the first thing you do is to convert these bits into binary in order to find out what each bit is doing. Okay, now when you convert this one to binary, I wish everybody could write, okay, 0, a hexadecimal, that is 0000, then 3 is 0011, and so on. Okay, can you write those? Maybe you can see what you get, but I would prefer that you write it yourself. Okay, now, so you expand that one. Every hexadecimal digit, you write 4 bits. And then you will get, we are just looking at this first instruction here, 03 to 600. Okay. Are we there? Hello?
Sorry, sir. I beg your pardon.
I was saying that a question can come and they give you a number like this one, 03 to 600. And they say, can you please tell us what that instruction is supposed to be doing? Someone will say that is a seek XE instruction. Explain what is being accomplished by that particular instruction, okay? And then I said that the first thing you do is to determine which format it is. Now we have said that it is a format 3 instruction. Then we try to interpret the bit by expanding it. Remember, those are hexadecimal digits. And we are saying that every hexadecimal digit is 4 binary bits, okay? So if we have 6 hexadecimal digits, we will have 24 bits. Now, this instruction here gives us what you get. I think the total here is 24 bits. Are we okay?
Yes, we are.
Okay. Then we can start interpreting the bits. Remember, The format is that the first 6 bits, that is the opcode. So when you expand these ones, you will see that the first 6 bits, they are these ones, 0, 0, all of them, they are 6 zeros. That is the opcode. Is that okay?
Yes.
Okay. Then the remaining bits, we can now say that maybe bit number 7 is N, bit number 8 is I, 9 is X, 10 is B, P is 11, E is 12, and then these other 12 bits, that is the displacement. Is that okay? Because that is what the format says. Opcode 6 bits, followed by the bits N, I, X, B, P, E, and then the displacement. Now you can see here, bit E is 0. You remember we said that when E is 0, then it means the format 3. So indeed, this is a format 3 because first of all, it is 24 bits, 3 bytes. Okay, that means the format 3. Or you can see that it is E is a 0, which means the format 4. But then when you look at bits B and P, bits B and P, B is a 0, P is a 1. So how do we calculate the target address when B is a 0 and P is a 1?
Target address is equal to the program counter plus the displacement.
Okay, very good. When bits B is a 0 and P is a 1, you take what is in the program counter and then you add the displacement that gives you the target address. Okay. Okay, very good. So you add what is in the program counter plus the displacement. Now let us add the program counter. They are saying here that it has got 3,000 because register B is 6,000. The program counter, they said it is 3,000. Is that right? So the program counter is 3,000 plus the displacement. Now, when you look at the displacement, these are 12 bits, okay? 0110 is a 6, then 00. So the displacement is 600. So we take 3,000 plus 600, and that gives us 3600. Is that okay?
So I beg your pardon.
No, I beg your pardon.
Pardon.
Okay, we said that we calculate the target address. We calculate the target address using bits B and P. And we said that when B is a 0 and P is a 1, that means the program counter. The target address is the program counter plus the displacement plus what is in register X. But what is in register X is only added when bit X is a 1. Now, when we look at this instruction, N is 1, I is 1, X is a 0, B is a 0, P is a 1. So when B is a 0 and P is a 1, okay? When B is a 0 and P is a 1, we have said that you take what is in the program counter plus the displacement. Now, contents of the program counter are given here. They are 00300. Okay. And then the displacement, we can see the displacement. These are the last 12 bits here. It is 0110000000. If you convert that onto hexadecimal, that is 600. So the target address is 3000, which is the contents of the program counter, plus the displacement, which is 600. And then we get the target address as what? 3600. Is that clear?
Yeah, it's clear now.
Okay. So the target address is here now. Remember the instruction is load the accumulator with. Now, what are we going to load into the accumulator? Is it the 3600, the target address, or contents? Because when you see the memory location, 3600 is here. Okay. And that memory location has these contents, 10300. Is that right? So what is going to be loaded into the accumulator is the question. Are we going to load the 3600 or are we going to load the 10300? Now you remember that that is determined by bits N and I. Bits N and I are the ones which tell us what we are going to load. Now in this case, N is 1, I is 1. So when we again look at the table here, when N is 1 and I is 1, we said that that is a simple addressing. Okay. The operand we take are the contents of the target address. Okay, when N is 1 and I is 1, simple addressing. The operand we need are the contents of the target address. Now we have calculated the target address is 3600, which is this one. Okay. So N is 1, I is 1. Therefore, the required operand is what? It is?
Contents in that address.
Contents, which is 10300. So that is the value which we are loading into the target address. Someone is saying that we are loading 3600, but contents of that one. And now here they are telling us the contents, 3600. These are the contents, 10300. So you can see that the value which is loaded into the accumulator is 10300. Okay. So is that first example clear?
Yes, it is.
Yes, sir.
Okay. Can you go through the next example? Maybe within like 3 minutes. They are telling us the target address is 6390. And what will be loaded into the accumulator will be 00C303. Can you try to calculate and find out that this is the target address and then that you are going to load that? You go through that one quickly. If you have a question, please don't hesitate to ask. Someone wants to be taken back to this bits which has N and I. We said that after calculating the target address, then the bits N and I are used to let us know what are we going to take as the operand, the address or the contents of the address. Okay. So we said if N is 0 and I is 0, it is the contents which we take. And we call that one simple addressing. But we said that the bits B, P, and E are part of the address bits. When N is 0, I is 1, it is immediate addressing. The target address itself is the required operand. Okay. Anyone who I is 0 is indirect. And you remember indirect addressing, you have a target address. Then the contents of the target address are also an address to another memory location whose contents you will take. And then anyone I1, that is also simple addressing. The contents of the target address is the required operand. Okay. Now, suppose you have that scenario there. Let us do the second part, 03C300, and we see whether we get that target address.
Show me the other table, the previous table. I want to confirm.
That one?
Yes, that one. I want to see the formulas.
Okay. You let me know whether you have got the answer or if you have got something different from what you have there, then we can explain. I hope you are working. Are you stuck? Or have you got the answer? Pamela has got it. One other person to let me know that it is okay. Okay, Eli, you are right. It is 6390. Then what are you loading into the accumulator? Because the instruction is 00. And the instruction whose opcode is 00 is LDA, load the accumulator. So what are we going to load into the accumulator?
We are going to take the contents of that target address because both values of I and N are one, so it's simple addressing.
So that's why you see here that value loaded into the accumulator is 00C300. 00C303 is the contents of this target address. Okay. Can you go to the other question? 022030. 022030. Very good. The answers are there, but I want to confirm that you get them. You understand how they are obtained. That is what is mostly important. Okay, I was saying that the answers are displayed there. The target address is shown, and then the value loaded into the accumulator is also shown. So we just want to confirm that you know how to get those values which have been shown there. Okay. Then do you understand why the value, what is loaded into the accumulator is 10300? Ellie?
Excuse me, sir.
Yes, please.
Would it be correct if I said for that part, we're using indirect addressing to determine the value into the accumulator, whereby the value of that target address I've calculated 30. It's the one which has its value is the one which has its value is the address of the operand. Does it?
You are right, because if n is 1 and the I is 0, okay, according to the table, if n is 1 and the I is 0, that is indirect addressing. The word at the target address, this is the something as saying the contents of the target address is the address. So the contents is the address of the required operand. Okay. So when you look at this one, you get 3030. Okay, 30 is here. Then if it is indirect addressing, contents of 3030 is the what? Is the address of the required operand. So here the contents is 36. So the memory location is 36 is the one which has got the required operand, which is 103000.
Okay, thank you.
Okay. Then someone is asking why.
Excuse me.
Yes.
Can you please come again?
Yeah, this is indirect addressing. Anyone who I is 0 is the indirect addressing. Okay. Now with the indirect addressing, when n is 1 and the I is 0, the contents of the target address, that is what they mean by word at the target address, is the address of the required operand. The word at the target address is the address of the required operand. So when we come here, the target address is 3030, which is this one. Okay. Now contents of the target address, which is 3030, is the address of the required operand. So you look for the address for memory location, which is 3600, and it is this one. Then its contents is the required address, is the required operand. That okay?
Okay. Yes.
Someone is saying, why don't we add the X? We said we add the X only when that bit X is a 1. Okay, but here in this example here, you see bit X is a 0. So it means you don't add the X. Is that okay? Can we go to the other one? 010030. We are doing I think it is question number 4. Example number 4, rather. Here is saying the target address is 30. Someone is asking, what do you load then? We said that those questions, what we are loading after calculating the target address are obtained from bits N and I. From the bits N and I. So in this case, I think N is 0, I is 1. N is 0, I is 1.
I think for that one, we take the target address to be the what?
So in this case, N is 0, I is 1, it is immediate addressing. So the required operand is the target address itself. So if you calculate the target address as 30, then it is what you take. I don't know whether it is clear. Is it clear?
Yes,
Yes,
sir.
it's clear.
Okay. Then can you go through those last two?
No.
Again, if whoever has a problem, please let me know.
So how are we getting the 30?
Come again?
How are we getting the 30?
The target address. So here they are telling us
Yes.
that to calculate the target address, we use the bits B and the P. So here B is a 0 and the P is a 0, which means that we are not doing any calculation. So according to this table, when B is a 0 and the P is a 0, that is the direct addressing, and the target address is just the displacement plus maybe what is the register X, but remember we said register X is only added when that bit X is a 1. Okay. So when you look at this table here, this question here, P is a 0, that means simple addressing, direct addressing, okay? Here, N is 0. So when you calculate the target address, this is a 0, 0, 0, 1, 1, I think is a 3, 0. So this is 0, 3, 0, which is a 3, 0. Because that is the displacement. They say the displacement becomes the what? The target address. And since here you have any 0, I1, okay? So that means that the target address becomes the required operand. Because N is 0, I1, that is immediate addressing. With the immediate addressing, the target address is the required operand. N1, N is 0, I1 is immediate. The target address is the required operand. So if the target address is 30, then it is the required operand.
Okay, I've got it.
Okay. Then can you go through the remaining two?
So pardon on the calculating the target address.
For which number? The previous one?
The previous one, why? Because when the B is a 0 and the P is a 0, the formula says we had the displacement and the X. But according to here, I'm seeing 30, which is meaning we only added the displacement and we never did X.
Because X is a 0, BTX is a 0. We said we only add the X only when that BTX is a 1.
Okay. Thank you, sir.
You're welcome. So can you go through the other two remaining examples and confirm that those are the answers you should be having?
Excuse me, sir.
Please.
I was wondering if your target address is, let's say, 3,600, and you find that it's indirect addressing. So in this case, the indirect address is 103.3000. But now this address doesn't have contents. What do you load then?
Maybe you are wrong. Maybe.
No, I'm just giving an instance. I'm saying, what if there is such an instance? What do you load then?
Well,
because in this case, the one doesn't have contents. So what do you write?
No, what I'm
not saying that.
What I'm saying is that according to the given information, if you are right, then that memory location should also exist and it should have some contents. Okay, so if you get something which is not, maybe you get a memory location which is shown, it would mean two things. Either the person who set the question did not give all the required information, or your calculation is wrong somewhere. It depends on the information which is given. If you are right, and the person who set the question is also right, then something, any memory location should have contents. Okay?
Okay, thank you.
Someone is asking, is the table always provided? I don't think we need those things. You can't forget those things, by the way. Because if, let us go back, bits B and P, I told you when B is a 1, it means the base. That means you are going to use the base addressing. So with the base, you add the register B plus the displacement plus X. When P is a 1, that means when P is a 0, P is a 1 and the B is a 0, P, that means it is the program counter which we take and add the displacement. The others, 0, 0, we said there is now no calculation there. The displacement, unless BTX is a 1, but the displacement is what you take as the target address. Okay? Then these N and the I think you can also remember. Any I1, any 0, I, immediate. Okay? So with the immediate, it is the target address which you take. Okay? Then any 1, I0, indirect. Okay? So that is where you take the word or the contents of the target address to be the address of the required operand. In cases both are zeros or both are ones, it is a simple addressing. So the contents of the target address is what you take. I don't think you can forget that. So that table is not provided. You mean the table for the accumulator? There is no table for the accumulator. What do you mean by table for the accumulator? The opcode, maybe
means this table we are seeing. This table we are seeing. This table where we're having the addressing mode, I think that's what she means. This table where we are having 3030, that this is the content in that address. Not this table, the other table in the question, this one. Yeah, that one.
Well, these are values which keep on changing because you need these values to calculate. So they will be given. Not the same values, but depending on the question. Because if it is a program counter, they have to tell you what is in the program counter, if this is the one you are going to use. If it is best, then they will let you know what is in their best register, okay? If you are going to use the X, they will have to tell you what is in register X. So the values of those registers will always be given. Not exactly this. This is an example. At any one time, register B will contain something else. Similarly, the program counter and the index register, okay? Similarly, the operation code is not always loaded the accumulator. It might be another question, okay? It might be another instruction. Load the accumulator is the one which has a 0, 0. Because according to the opcode here, it is 0, 0. That's why we said that the question is loading the accumulator with whatever we are calculating. Okay, so I was asking whether someone is asking what if we write the target address as 0030 for question 4, that is fine. That is fine, but the address in most cases is written under the word. They are all 24 bits, but it is okay. It is okay. After all, we know whatever comes in front of an integer, any 0 in front of an integer does not carry any meaning. Okay, quickly, the last two, just to confirm that we have got it. I would want to let me know whether you are through so that we can continue.
Excuse me, sir. Excuse me, sir. We cannot hear you.
Okay, I'm listening now. I hope you can hear me now.
Let's go back to the previous table. Yes, we can hear
Yes,
you
can
now.
get you.
Yes, I would like to ask you about this when n is 0 and I is 0. What do you mean by here by operand is equal to contents of target address in bracket bits P and A are part of the address bits? What do you mean by that?
Okay. Now, first of all, when n is 0 and the I is 0, okay, the same case is when n is 1 and the I is 1. In both cases, it is the contents which we take, okay? In both cases, n is 0, I is 0, n1 or I1, in both cases, it is the contents. But we are saying that for n is 0, I is 0, those bits B, P, and E are not used for calculating purposes. We don't use them to calculate the target address, but they are just part of the address. So when you append those bits to the displacement, it becomes the address. So in this case, you get an address of 15 bits, which becomes the target address.
Okay, thank you, sir.
Is it okay? Because now let us look at this particular example. Bits BP, they are zeros, okay? So we are not going to take base register plus displacement, okay? Because both are zeros, even these bits are going to be, the bits B, P, and E, they are part of the address. So this time we have an address which is, that is a 6, maybe 3, 6. It is because these bits 0, 1, 1, that is a 3. So we have 3, 6, 0, 0. So that becomes the address. You don't do any calculation. If the bits N and the I are 0, then the bits B, P, and E are part of the displacement, which becomes the address. Is that okay?
Yeah, yes.
Okay, then can we do the last one? Okay, that is correct. Then what are you loading into the accumulator? Okay. Okay, very good. So that is how we usually calculate. But then there is something I want you to understand, if you can pay attention. The operation code is always given using 2 hexadecimal digits. It is always given using 2 hexadecimal digits. Okay. Now, if it is given using 2 hexadecimal digits, it means that when you expand them, you get 80 bits. Okay. But then it is only format 1 and format 2 which use 80 bits. Format 3 and 4 use 6 bits. So one might wonder which bits are you going to scrap off in order to remain with only 6. Now, in most cases, it is the last 2 bits which you usually eliminate. The last 2 bits on your right, they will always be zeros. So if you have a format which wants 6 bits and the instruction and the opcode is given as 80 bits, it means that when you come to write the machine language instruction, you have to use only 6 bits. So it is the last 2 bits which you eliminate, the last 2 bits on your right. We will see such examples in the future. Okay. Now the instruction set. Okay. We have been talking about instruction formats. Now the instruction set is similar, only that we have got more instructions here. So all of the instructions that we saw with the simple seek, ladies and gentlemen, if we have to move, I think we have to be attentive. Let me repeat, okay? I said that usually the opcode is 2 hexadecimal digits. Now, 2 hexadecimal digits, that means 80 bits, because every hexadecimal digit is 4 bits. So if the opcode is given as 2 hexadecimal digits, that implies 80 bits. Okay. Now we said that format 1 and format 2, they use 80 bits, so that is okay. But format 3 and 4, they use 6 bits. The opcode is 6 bits. So if you want to interpret the instruction well, it means you have to remove some 2 bits, because the operation code will be given with 80 bits, but the instruction format accepts only 6. Now, I said that it is the last 2 bits on your right, which are usually eliminated. And those bits will always be zeros. Is it clear now? Hello?
Yes.
Okay. Now, I was saying that when you come to the instruction set, all of the instructions which we saw for the standard version, the simple seek, they are also used in the extended version. But the extended version has got more instructions. The other one has less. For example, since okay, I'm saying that, for example, since we saw that this time we have got more registers, like you remember, we have register B, register S, register T, and the floating point accumulator, which is register F. Okay, I hope I'm clear now. I'm saying that since we have got more registers, it means we also have more instructions. So an instruction like a load register B, store register B, add the float, subtract the float, multiply float, divide the float. So these instructions exist in the extended version. Okay. Then we have instructions which work on registers, because the simple seek does not have instructions which work on registers. Remember, for the simple seek, okay? So I was saying that since we have got more registers, we have more instructions as well. So we have instructions like load register B, load register F. Okay, load is all store. Here we are using registers. Okay, and then since we have got a format 2, where we have an opcode and then the operands are registers, we can have like these instructions like a register move. So this one acts like the move in the Intel 8085, where you move contents of one register to another register. Here we say register move. Okay. Then we have instructions like add the registers. That means you are adding what is one register to what is in another register. We have subtract registers, multiply registers, divide registers, and so on. Yeah. Yes, I will. Someone is asking, requesting me to load these ones on Muere. I will. And then I will also send the slides to the class rep for you to share. Now, the directives, you remember? The directives, the directives, we compared them to like declarations and assignments for the high-level languages. Okay. So we said that if you remember, with the Intel 8085, we had 3 directives. We had the define storage, define byte, and then define word, DS, DB, and DW. So instead of defining storage, these guys say reserve word, because they are reserving data which is going to be used. They are reserving storage. So they say reserve word. Okay. Then if it is a character, they say reserve byte. Okay. When you are putting information into those reserved area or the reserved bytes, you say word if it is an integer, or you say byte if it is a character. Okay. Then we have got instruction directives like a start. Whenever you are going to begin a program, you say start. And then the program has to end with the what? With the end. Okay. So sometimes I ask people I can give you a directive which is in Intel 8085, and then I can ask you, how will this same instruction be executed if I were using the seekxe? Okay. Okay. Now the instruction is set. Usually when they give you the instruction set, you will find that some characters will be given in uppercase, while others will be in lowercase. Okay, now when you find a character M, that means you are talking about a memory address. A small n indicates any integer between 1 and 16. Then where you talk about R1 and R2, those are registers. Again, when we put things into brackets, that means the contents. Okay, so that means the contents. Now, for example, if I write M blah blah up to M plus 2, it specifies that you are going to put contents of a given memory location into the accumulator. There we are given a memory location M up to M plus 2. Remember, we said that any integer occupies 3 bytes in memory. Any integer occupies 3 bytes. So it means that if, for example, byte number 1, the first byte, let me say if it is a 5, then 5, 6, and 7, I am just giving an example, that if you have a memory location beginning with 5, and the integer is going to consume 3 bytes, then it means bytes 5, 6, and 7 are going to be used to hold that integer. So that's why we are saying that M up to M plus 2. So in this case, my M is a 5, M plus 2, of course, is a 7. So the memory location is from M up to M plus 2. That means the contents of that particular memory location. Okay. Now, when I write that and then I put that arrow pointing to the left and I put A, it means that the contents of those particular memory locations, which are 3, their contents are going to be put into the accumulator. Okay. Then the reverse is also true when we store. When we store, you remember storing, we take what is in the accumulator and we store it in memory. Okay. So here we have contents of register A, they are stored in memory from memory location M up to memory location M plus 2. Okay. Where you find a P, that would mean a privileged instruction. You know that, I think you know what we mean by privileged instructions. Mostly these are instructions used by the system, or they are used in special cases. Okay, X would mean that that particular instruction applies only to the XE version. If you find an instruction where they put a comment X, it means that that particular instruction applies only to the XE. The simple version does not have such an instruction. Where you find an F, it means that you are going to use a floating point accumulator. That particular instruction is using a floating point accumulator. Okay. And where you find the CC, those are condition codes. That means those when that particular instruction is executed, some flags will be raised or they will be set. Okay. Now, what you see there is the format, the SIG-XE instruction is set. Okay. Now, let me go through some of these if you can pay attention. Let us look at the first instruction. The first instruction is just saying add M. Okay. Now we said that adding, you take what is add the M, and when they write M, we said that that means a memory location. It means that you are taking what is in memory, and in memory, you remember we are talking about those 3 bytes in memory from M up to M plus 2. So you pick what is there, and you add it to contents of the accumulator, and the answer stays in the accumulator. So that one, if you can look at that, its effect. Okay, we are looking at instruction number 1. If you look at its effect, it is saying that you pick contents of a memory location M up to M plus 2, and then you add that to what is in the accumulator, and the answer will stay in the accumulator. Okay, so that instruction can be a format 3 or a format 4. In that column where they are saying a format, they are putting 3/4, meaning that it can be a format 3 or format 4. Because since we are saying that it is the RDM, it means that we are accessing memory. And we said that instructions which access memory are format 3 and a format 4. Now the opcode for format for RDM is 18. Okay, those are hexadecimal digits, 18. Okay, then you can have RDF. RDF, that means we are going to use the floating point accumulator and the memory location. So a floating point number, like you remember, we said occupies 6 bytes, not 3. So that's why we are saying that it is from M up to M plus 5, which is 6 bytes. So you take a number which is there plus what is in the floating point accumulator, and then the answer will stay into the floating point accumulator. When you look at the notes, they are saying it X and F. Like I said, the X means that it is only used on the XE version. The simple seq does not have that instruction. And indeed, you remember the simple seq doesn't have a floating point accumulator. It is only the extended version. Okay. F means that you are using the floating point register. Then add registers R1 and R2. So we are saying that that is a format 2 instruction. Someone is saying, why doesn't RDM have notes? I don't think the notes, remember we said that we have X, F, or C. Now this one, it can be used either in format 3 or format 4. It can be used either in format 3 or format 4, and there is nothing special about it. Okay, yeah. Then add the F, there is an X there, which means it is only for the seq XE. So I think that is important that they alert you that. Then when you look at instruction number 3, add the registers R1 and R2. Of course, we said that that is a format 2 instruction because it is the one which has got your code, and then register R1 and R2. The code is 90, and then it is adding contents of register 2 to contents of register 1, and then the answer is in register 2. So you should note the direction. So here we are adding R1 plus R2, and the answer remains in R2. Okay, so we first mention R1, then we mention R2. It is important that you note the what? You note the direction. And then in the notes there is X, which means that that is just a what? It is only on the extended version, because the simple version, it does not use registers. It uses only memory. And then you can, I think, interpret any instruction. You can interpret any instruction after that. Okay. So we don't have very many. I am not asking you to cram them. In case you need any of these instructions, of course, you might need them, and then the opcodes will always be given. Is that okay?
Yes, it's okay.
Okay. So next time, I think we are going to stop here because this one is going to take us some time. Next time, we are going to do some simple, what? Simple programming using the assembly language programs, using the what? Using the XE or the simple seek. Simple seek and then the XE instructions which we have seen. Okay. You can meanwhile go through these ones, but we will explain later when we meet next time on Friday. Okay, so I beg that we stop here today. Is that okay?
Yes, thank you for the lecture.
Okay, I'm going to send the recorded lecture and the notes to the class rep. And when I am ready, I will also load the same on Muere. Okay. Okay, have a nice afternoon.
Thank you. Likewise.